Now let's move on to talk about yield criteria, and with a focus on metals. Some observations for metal yielding includes that the plasticity in metals is mainly caused by shear deformation, and the influence of hydrostatic pressure is very limited in most of the common cases that we see. Therefore, when we try to formulate a yield criteria based on the current stress state, the general form is that a function of the stress state equals to 0. Then, since our observation has shown that the hydrostatic pressure's influence is negligible, we can decompose our Cauchy stress into two parts. One is a deviotic part, and the other one is hydrostatic part. And the tau p can be written in this form, where trace of a tensor is the summation of the diagonal terms of it. So this is basically a equivalent hydrostatic pressure given by 1/3 of a trace of tau. You can imagine applying the actual hydrostatic pressure state to a material, then you would have tau being minus p times identity, and 1/3 of the trace would be simply minus p, which is your amplitude of pressure. And in the general case, this is an equivalent amplitude of hydrostatic pressure. Then the deviotic part of the stress tensor is simply the total stress tensor minus the hydrostatic part of it. Our yield criteria should be focused on the deviotic part of the stress tensor. For this, a very simple approach is simply to calculate the amplitude of the deviotic part of the tensor. And when we calculate amplitude, we take the dot product between the tensor and itself. The scaling factor of 3/2 is to ensure that when we have a uniaxial stress state, this whole thing would then return to just the uniaxial stress. So then we revert back to one-dimensional case. This is the so-called von Mises stress. We can write it in indicial notation as such. And this whole term divided by 2 is called the second invariant of the stress tensor. It's sometimes denoted as J2. And we can write in principal stress state that the von Mises stress equals to this expression. So tau 1, tau 2, and tau 3, they are the three principal stress components of our stress tensor. Then our yield criteria is in the very same form as in the one-dimensional case, except now we replaced sigma 1 with sigma von Mises. So as I mentioned, if we just have a uniaxial stress state, then sigma von Mises through this scaling factor and this expression would then result in the same being the same as sigma 1. We can plot it in two-dimensional case. Let's say we only have tau 2 and tau 3 and tau 1 equals to 0. This is a plane stress problem. Then this expression would result in an ellipse, generalized ellipse. In three-dimensional, it is a cylinder with the axis being this line represented by tau 1 equals to tau 2 and equals to tau 3. And it's very often in plasticity that we look towards this plane. Along this line, be able to observe such so-called pi plane. We have the three axes and we retrieve a perfect circle. And the radius of the circle is related to the yield strength by a factor of square root of 2/3. So basically, this yield criteria sets a boundary between elasticity and plasticity. So within these circles, we have the material being purely elastic, and once we go beyond this circle, then the material will have plastic deformation. Besides von Mises, there are other yielding criteria, such as Tresca, which is also very popular for metals. However, compared to von Mises, Tresca criteria, first of all, is more conservative. It lies within the envelope of von Mises criteria. Secondly, it has corners. This is, however, undesirable for numerical implementation because numerically we would like to have continuous, well-defined tangent and normals on this yielding envelope. This is not the case with Tresca. There are other yielding criteria for other materials where the effect of hydrostatic pressure is important. For instance, for soil, rocks, concrete, and ceramics. These criteria such as Moore, Coulomb, and Drago-Praga are well suited for this kind of materials. For aerospace applications, we are more interested in the plasticity theory for metals, and hence Vomises is the best choice for us.